All right. Today what I want to talk to you about is a method of estimating roots of a function. And this is using something called Newton's method. And Newton's method basically says if I've got a function and I know there's a root and I want to find it, what I can do is I can pick some guesstimate. I'm just going to say, hey, you know what? I think maybe it's right there. And I'm going to draw a tangent line and I'm going to calculate where that touches. And now that gives me a closer value. So if I zoom in on this little square, now my function looks like this. And there's x1. And now what I do is I draw a tangent line at x1. And it's even closer. That's x2. And I can just keep doing that over and over and over again. And every time I do it, I'll get a little bit closer, except under certain circumstances, which we'll talk about a little bit later. And eventually I get close enough by just redoing successive iterations of the calculation, that I get to where my number's not changing within the number of decimals that I care about. So what does that look like mathematically? Okay, thing one, let's clear that. I don't know why that was on there. Mathematically, let's linearize. We've got a guess at x sub 0, and I will linearize at that point. So I'm going to have a point x sub 0, f of x sub 0. There's my point. And if I take the derivative, I can calculate the derivative at that point. And the linearization at x sub 0 is equal to the derivative, or slope, times x minus x sub 0 plus f of x sub 0. And what I'm looking for is I'm looking for where does this line cross the x-axis. That's my first, if we go back to, if I go back a screen, that's my x1. Where does that linearization cross the x-axis? So in other words, I'm going to make this line equal to 0. Which makes my x value x sub 1, the root of the linearization. All right, let's solve for x sub 1. I'm going to subtract the function, divide by the derivative, add x sub 0, and I get that x sub 1 equals x sub 0 minus f of x sub 0 over f prime of x sub 0. And obviously, I could do the same thing with x1 and x2, x2 and x3, x3 and x4. And I can extrapolate that out to say, well, the next value will be the previous value minus the ratio of the function to the derivative of that previous value. So there is Newton's method in a nutshell. I'm going to make a guess, and then I'm just going to do this over and over and over again until my numbers stop significantly changing. So let's do an example, and then we'll talk about when it failed. All right, let's do an example. Solve x cubed plus 3x plus 1 equals 0. I know that x sub n plus 1 equals x sub n minus the function x cubed plus 3x plus 1 divided by the derivative 3x squared plus 3, and these are x sub n. And I need an initial value. So x sub 0 equals, and I'm going to choose -1. And the reason I'm going to choose -1 is that if I look at just a plain old y equals x cubed. I know it looks like this. I know that if I put in a negative value of x, that it is going to become a negative. For example, if x equals -1, this is a negative number, which means that the transformed function will look something like that. And I'm going to say, okay, my initial guess is -1. And since it's going to converge, it doesn't really matter as long as your guess is somewhere in the general vicinity. So what does x sub 1 equal? Well, x sub 1 equals -1 minus -1 cubed plus 3 times -1 plus 1 divided by 3 times -1 squared plus 3, which equals -1/2. So what does x sub 2 equal? Well, -1/2 minus -1/2 cubed plus 3 times -1/2 plus 1 divided by 3 times -1/2 squared plus 3, and that's approximately -1/3. And x sub 3 will be equal to -1/3 minus ... And what we get for x sub 3 is -0.322222, 1, 2, 3, 4, 5, 6, 7, 8, 9, because that's what my calculator goes to. And so then I'll plug that in, and I'll find x sub 4 equals -0.3222222, ... minus, and then that equals minus stuff -0.322185355. Notice the 4 decimal place is the same as the previous answer. X sub 5 equals, doing the same thing, -0.32218535546. Notice 18535, the same answer. 2, 1, 2, 3, 4, 5, 6, 7, 8 decimal places. And we could do it again and again and again until we get to the point where either our calculator is not showing us any changes or our answer is as accurate as we want to be. If we only need 3 decimal places, as soon as we get to x sub 4, we notice that to 4 decimal places or 3 decimal places, my answer doesn't change from x sub 3 to x sub 4, which means that I could say that the root of this function, accurate to 3 decimal places, is x equals near -0.322. All right, if you are in my class, go ahead and do exercise number 53. I am going to stop this video here and come back with part 2, which is failures and a few notes on how to do this more efficiently.